This is an applications presentation of laser shearography being used for rotor blade NDT inspection within the wind power industry. Laser Shearography NDT is used extensively in the wind power industry by both OEMs and service providers for the inspection of defects within rotor blades. Typical defects or quality control measurements that laser shearography can be used for inspection include ply wrinkling, disbonding, crack cause, impact damage, and bond line length measurements. Laser shearography can be utilized to detect defects within seconds, achieving inspection rates of multiple square meters per minute. Presented to the right in Figure 1 shows a schematic diagram of a rotor blade with a dual spar cap design. Typical defects that can be detected by laser shearography NDT and their usual location is depicted. Here is an overview of laser shearography applications used for rotor blade NDT. Application A is an example of ply wrinkling found within the spar cap. Application B, disbonding within the leading edge protection, also known as the LEP. Application C is crack cause within the trailing edge. Application D, disbonding within the trailing edge. Application E is an impact damage from a hailstorm on the trailing edge. Application F, impact damage caused by a lightning strike on the trailing edge. Application G, bond line disbonding on the spar cap. And Application H, a bond line length inspection of the leading and trailing edge. Ply wrinkling. Since 2010, laser shearography NDT has been used for the inspection of ply wrinkling within spar caps. Ply wrinkling causes complex stress concentrations within the ply layer that can compound over time, leading to eventual failure of the blade. The formation of wrinkling occurs in the fabrication of monolithic laminates and in the joining of laminate sections. Within a monolithic laminate, wrinkling can be caused if the fiber alignment of the plies is not purely in plane, i.e., the plies are not flat or straight with respect to one another. Alternatively, they can be caused when shearing forces are created during the section joining process as a result of thermal mismatch of the coefficient of thermal expansion of the composites and/or tooling. The term ply wrinkling is a broad defect description that relates directly to the fiber waviness and/or ingresses of resin pockets. Laser shearography is the only NDT technique that can completely detect ply wrinkling, both fiber waviness and ingresses of resin pockets, since the technique measures the structural reaction to outer plane bending. Using other NDT techniques, for example ultrasonics, only ply wrinkling caused by ingresses of resin pockets can be detected. Ply wrinkling can be uniquely identified in phase maps as multiple wave-like black and white fringes shown to the top right-hand corner. In spar caps made from monolithic carbon fiber CFRP laminates, the inspection of ply wrinkling can be detected using static mechanical bending via reaction measurement of the spar cap to an applied bending moment, typically at the blade tip using either a floor hunter or floor explorer system. Figure 1 below shows a 2D phase map image of sections with visible wave-like fringes showing evidence of ply wrinkling. In Figure 2 we see an image of ply wrinkling inspection being performed using a Q810 at an on-site inspection. In spar caps made from monolithic glass fiber or GFRP laminates, the inspection of ply wrinkling can be detected using vacuum partial excitation via application of a high pressure differential using a floor hunter or floor explorer system with a manual vacuum hood, or alternatively via thermal ambient cooling via measurement observation of the laminate during cooling using a floor explorer. The video above is a 2D phase map recording of a live measurement using thermal ambient cooling. As can be seen, the indications of wrinkling are visible with the white and the black fringes. We apply a reference, step measurement, and then multiple snapshot measurements, instantly inverting the images. Disbonding of the leading edge protection, or LEP. In order to protect the leading edge of a rotor blade, an additional protection coating, also called an LEP, is applied, which can consist of either a metallic shell, polymeric coating, or thermoplastic shield. If the LEP becomes disbonded from the leading edge as a result of manufacturing error or in-service conditions such as high temperature, humidity, and moisture, the aerodynamic performance of the rotor blade will reduce. Laser Shearography NDT is a quick inspection technique that can reveal the presence of disbonds between the LEP and the leading edge within seconds using thermal excitation. Figures 1, 2, and 3 show a 2D phase map image of the LEP with visible fringes showing evidence of disbonding. Cracked cores within the trailing edge. Cracked cores within the trailing edge of a rotor blade is often attributed to torsional overloading or transportation damage. Usually, visible bumps appear in the rotor blade surface where the core has potentially cracked. Upon inspection of one rotor blade, a Q810 floor hunter was implemented using vacuum partial excitation. Inspections showed that the trailing edge had 2 cracked foam cores totaling 4 meters in length, presented here in Figure 2. Other inspections of rotor blades using a floor explorer using thermal excitation has also been performed successfully for the detection of cracked cores. In Figure 1, we see an image and localization of a cracked core on a rotor blade using a floor explorer with thermal excitation, and similarly also in Figure 2. Disbonding within the trailing edge. Many applications involving laser shearography are inspections performed post-production in quality control of the trailing edge for disbonding between the core, i.e. foam or balsa, and the skin laminate. Using either thermal or vacuum partial excitation, disbonding can be easily detected using laser shearography. The internal core structure is clearly visible in the respective phase maps. In many instances, the use of ultrasonics will not work for this application. Impact damage resulting from a hailstorm to the trailing edge. In-service inspection of rotor blades is often performed up tower. Invisible impact damage cannot be detected easily using other NDT techniques, but for laser shearography this is a quick and simple process using either thermal or vacuum partial excitation. In this case, a hailstorm out at sea resulted in impact damage on the trailing edge of a rotor blade, causing multiple identifications of internal crushed foam cores. Impact damage caused via a lightning strike to the trailing edge. An inspection was performed of a rotor blade damaged by a lightning strike. Whether or not the blade could be repaired was evaluated through assessment of the affected area using a Q810 floor hunter using vacuum partial and thermal excitation. The extent of visible damage is larger than the visible marked indication. After assessment, it was determined that the rotor blade could be repaired using glass fiber composite resin patching. In Figure 1, we see a 2D phase map overlaid on a marked image of the lightning strike point of image, indicating multiple fringes of structural failure. In Figures 2 and 3, we see marked images of the lightning strike point of impact and the Q810 system. Bondline disbonding On the spar cap. In this application, the object under inspection was a carbon fiber monolithic spar sprayed with developer. Inspection of the spar cap bond line between the outer laminate gel coat and the CFRP monolithic laminate spar cap can be performed using the Floor Explorer and thermal excitation. In the video presented to the right, we use two 1000 watt spot halogen heat lamps for a heat duration of 20 seconds. Waiting another 10 seconds afterwards, we can see the localized disbonding fringes between the gel coat and the spar laminate. The bond line length inspection of the leading and trailing edge. Inspection of the leading or trailing edge bond line can be performed easily using the Floor Hunter laser shearography system. Often this inspection is not related to the assessment of disbonding, rather a quality control check that the cross-sectional length of the bond line is higher than a certain tolerance. The top phase map image is that of the leading edge. The bottom phase map image is a representation of the trailing edge. Thank you for your attention. If you have any questions or comments regarding the applications of Laser Shearography NDT, please contact Dantec Dynamics.